So here, our question of the section is how to perform integration of a vector field. And here we just denote the components to be P, Q, and R for the vector field. So basically here, we want to establish the integrals. So recall, it's always the problem of how you set up or just define the integration on the object. Okay, so recall when we have seen several integrations now. So the definite integral for a univariate function, right? And then we extend it to the definite integral for a vector function with univariate with a single variable t, right? And then we have seen double integral for a variable function over some region cap D, and we subdivide the area in terms of dA. And then we have seen triple integrals of a function little f over some solid. Okay, and then the subdivision is now the volume that we see, right? So something common about these integrations is that okay, we always have the form where we are doing the integral, but here we integrate it over something. Okay, so it can be an integral. An interval from A to B in one variable, or it could be a region, or it could be a solid. But here I'm just gonna put it as a red square symbol right there, as it just represents something, okay, some region. And then we're integrating some function. So that's little f or vector function or whatever. And then finally, what's important is about that d notation. Okay, so it's going to be the way that you increment the red box, the red square, right? So it's the way that you subdivide. Okay, so I'm going to put star here to indicate. Okay, so the region, right, in the red square is one important feature, and then that's the way that we subdivide, but this part, that d something is also important. Okay. And as long as you establish these two, and then you are good to define all kinds of integrals. Okay. Now for our section, we want to also recall another way of writing a definite integral. Okay, so basically, when you see the definite integral from A to B of f prime, so naturally you can think about the fundamental theorem of calculus. But here I want to mention that another way to think about this is that okay, this is f prime times dx, right? So you can always think about the u substitution. But if you don't really write out u, you can just put it as d f of x. Yeah, just the differential symbol. Okay, the differential notation. Okay, so this is a way that helps you to interpret the information from this section further. So this is the differential notation. Now recall the divergence of a vector field is what? It's actually nabla operation, nabla operator starting with the vector field. So basically, if you recall, so this is the vector of operators that composes the partial derivative of x on the first component, partial derivative of y on the second, partial derivative of z on the third. So this is exactly del x of p plus del y of q plus del z of r. So in a way, you see, this is a way that you are doing the partials, right? So this is really related to the differential that we have been talking about. So the idea here is that maybe we can define the integrals in terms of the vector field using PQ and R. Okay. Because here, when you look at the divergence, this is doing the partial derivatives component-wise to these components of the vector field, PQ and R, right? So this is doing a different partial derivative for a different component. So when you're doing the integral, you possibly think, okay, we probably can do a similar thing. So we integrate component-wise. So it's just every component PQR, we're just gonna integrate in terms of X, Y, Z, respectively. Okay. In terms of the notation, this is a component-wise integral. And also recall. So we have seen dx, dy, dz before. Okay. So if you recall, when we talk about the vector function, we know that so for vector function with x, y, z of t as components, right? So this the differential is actually x prime of t plus y prime of t plus z prime of t whole thing times dt, right? And this part is actually the tangent function, right? So r prime. So when you write dr as a vector function, this is r prime dt, right? This is something just the same idea as that differential notation. Okay? So now we can somehow see that we can put things together. So basically, you see we have P, Q, R that are the components of the vector field, right? And then dx, dy, dz, they are related to the components of the tangent direction of a vector function. Okay? So now this, in a sense, this is a vector inner product, dot product. We can now introduce the notation as follows. So when we talk about p dx plus q dy plus r dz, so you can write it as an inner product, a dot product. So pi plus qj plus rk, starting with I dx plus j dy plus k dz. Okay. So basically separating the products of these component functions and the differentials in different vectors, right? And of course, the first part, this is the vector field. Okay. And then the second part, we know that in terms of the differential notation, dx is actually x prime dt, right? If we were treating this as a vector function, so dy is y prime dt, and finally dz is z prime of t dt, right? So then this can be written as the vector field starting with. So we just replace. So this is at every component we have x prime, y prime, or z prime. But then everything follows with a dt. So we put them together. So this is x prime of t I plus y prime of t j plus c prime of t. Okay, and we in a way we factor that dt at the end. Okay, and now we just see that okay, that's actually that's our prime of t that we have. Okay, which further reduces to dr. So this is f starting with dr. So now, okay, so when we want to integrate this pdx qdy rdz, right? So essentially, what do we see? We see this is the vector field, starting with the way that you increment along a vector function. Okay, so these are both vector. These are both vector fields, of course. So the vector field that f is let me think. Yeah, so vector field f is definitely a vector field. dr is actually you can say it's a vector function. So in a sense, they are both vectors that they can be doubles. Okay. Thus, we may introduce one type of integration so basically we're integrating over still we want to specify the region, okay, the red square, but then we are integrating exactly just the vector field starting with the increment of the vector function. Okay. And if you're looking at this vector function, you always parameterize it from A to B for that variable t, right? So this is exactly vector field starting with r prime of t bt. Okay, so just the tangent direction along this vector function. Okay. So once again, recall we have been talking about the vector function for quite a few times. So this r of t equals to x of ti plus y of tj plus z of tk, where we have the parameter t from A to B. This introduces a curve, right? We used to call it C in the three-dimensional space. Okay? This just tells you. So now, actually, what are we doing here? Basically, we have a curve, cap C, which is parameterized by this vector function. Okay? And then you see, essentially, you are integrating everything on this vector function. So now the variable goes from A to B, and now you are just doing the tangent direction r prime, starting with the vector field f. Okay? So essentially, you are integrating over this curve. So that the red box can be replaced by C. Okay? This curve C. So definition. That's cap f be a continuous vector field, and cap C be a smooth curve defined by the vector function little r t, and t goes from A to B. Then the line integral of the vector field along the curve C is the following. So basically, it's actually the equation on the top in quotes, except that the red box is now replaced with the notation of the curve. Okay, so this is the integral along the curve C of f starting with dr. So the calculation is exactly the integral from A to B of f. So now notice that here we only look at the behavior of the vector field along the curve. So this is f evaluated along the vector function. Okay. So that's the evaluation of the vector field. Now we start with the tangent direction, and then dt. Okay. Incrementing along the curve. Okay. So now we somehow motivated this line integral. Example. So let's say our vector field is f of xyz equals to xyi plus yzj plus zxk, and c is given by the following vector function. This is r of t equals to ti plus t squared j plus t cubed k. And t is between 0 and 1. Now we want to find the line integral. So when we want to find the line integral, we just need to be really specific about the right-hand side. Every piece of information on the right-hand side of the box equation. Okay, so it's the integral from A to B. Okay, that's something not new. dt is just saying, okay, it's the integral in terms of t. All right. So basically, you see that we're integrating everything in terms of t. So that's something you need to be careful about. Okay. So there's the evaluation part right here, and then that's the tangent direction part for the curve that you need to calculate. Okay. So and then we need to dot. So let's do that systematically. So we have RT, that is, so if we write in terms of the component functions, then just by matching the components, okay, so basically we know x here must be t, okay, x of t, so yeah, let me put in the next line, where x of t must be t, y of t must be t squared, z of t must be t cubed. Okay, just helping you to identify those components. Okay, this tells you, okay, basically when you do the evaluation, what x, y, z should be. Okay, so f, the vector field along the curve is, so x of t, y of t, I. So just by looking at the definition of the vector field, so this is x, y, I plus y, z, so it's y of t, z of t, j plus z of t, x of t, k. Okay. And then we just do the substitution. So x is t, y is t squared, so t times t squared I plus, so t squared times t cubed j plus t cubed times t k. So this becomes t to the 3i, so t to the 5j plus t to the 4k. Okay. So this component-wise substitution. Right. So that's the first part of the right-hand side of that equation at the top, right? And then we calculate our prime. Also, our prime of t equals to. So now every component is a polynomial function in terms of t. So that's simple. Okay. So it should give you, so t gives you 1 as the derivative, 2t, t squared gives you 2t as the derivative, and t cubed gives you 3t squared. And then we do the dot. Hence, the line integral of f dot dr. So this is, so basically from A to B, this is integrating from 0 to 1, f of r of t, evaluation time starting with the tangent direction. And now we can just do the dot based on the two parts that we have from above, right? So this is the evaluation of the vector field starting with r prime. So we just do component wise. So this is inner product, dot product. So t cubed times 1, t cubed, plus t to the 5 times 2t. So that's 2t to the 6. Plus now t to the 4 multiplying by 3t squared. That's 3t to the 6. Right. Easy. And then, so far so good. Okay, looks good. Then we just combine things. So these are just numeric expressions, right? So t to the 3 plus 5t to the 6. Okay. So the answer here. So let's quickly do that. So add 1, divide the rest of power functions. 1/4. So plus 5 over 7 t to the 7 evaluates, and now we specify that we are integrating with respect to t, so we are evaluating t. Okay. So now you see, okay, we have more and more variables. We have in the previous chapter we have x, y, z, right? Now we are now introducing t. So we need to be very careful about the specific variable that we're dealing with. Okay. So the evaluation should give you 27 over 28. Okay. So as long as we define this integral in a reasonable sense, then the calculation is also, it should be clear. Okay. Remark. So now everything relates to vector functions, right? So we are now looking at r prime, right? So r prime is the tangent direction. So a very important and highly related concept is the unit tangent direction, right? Recall that unit tangent direction, T is the normalized tangent direction. So basically, you just use the tangent direction r prime to divide by its magnitude. That's the unit tangent direction. And also, you recall that the magnitude of r prime is actually ds dt, where little s is the variable representing r length. Okay. The arc length is the distance that you travel along. If you recall. So to be reminded, this is 17.4, 14.4 section. Hence, so when we write down the line integral, so we are writing the equation again. But now, if we are able to write r prime in another way, okay? So the tangent direction is now so r prime is from the equation on the right above on the left hand side. R prime is actually the magnitude times the unit tangent direction, right? So unit tangent direction multiplying by the magnitude of r prime. And now we follow by dt, okay? So this substitution, and we can do even further because this part, from the second equation above, this is exactly dx, okay? this is the increment of our length. Okay, so now if we change the variable, so this is actually what? This is actually, so this is ds. Okay, then the whole integral becomes integrating along the curve with respect to the arc length. So I'm putting the curve C back. So this is integrating along the curve with respect to the arc length of what? Of f starting with t, cap t. So this is the vector field starting with the unit tangent direction. Okay, so you can think about it as well. This is thinking. You can think about this as okay. I'm traveling along the curve, so the tangent direction, the unit tangent direction is exactly the direction that you're traveling along the curve. You dot with the vector field, so it's sort of like the force starting with the displacement. Okay, so this unit tangent direction multiplying by the arc length increment. This is like accumulating the work. Okay, so remark. So in the physical sense, so if you have, let's say we are having a object, so and this is moving along this the ground, let's say, and there's a force applying to it. Okay. So we know that the work equals to the force as a vector starting with the displacement. Right? That's a vector. And basically, if you accumulate the work, this is just accumulating the force at every location, starting with the tiny increment of the displacement of the object. Okay. So indeed, consider a vector field F that describes a force field and a particle that is moving along a curve C. So basically, let me quickly illustrate what happens in the two-dimensional plane. So here, I'm just gonna sketch a vector field. So basically, at every location, you will have a assigned vector, and that's the force field. And then you have a curve. So that's this method, right? And the way that you're accumulating this movement is actually you can for integral, this is subdivided into pieces. So the idea here to quickly mention this is you can break it into little segments, right? And at every tiny little segment, what you are doing is okay, you have, let's say, the tangent direction like this. That's the unit tangent direction, which is cap T, okay? And at every location, this vector in back, that's about the force field. Okay, so cap F starting with cap T, and then ds is actually the tiny increments along the curve. Okay. So if you accumulate everything, this is exactly the work done by moving the particle along the curve within the force field. Okay. We're talking about the work if you travel along a purple curve like what's in the picture, okay? That you accumulate. That's basically when we're doing this kind of definite integral, it's always that Riemann sum, that kind of accumulation that we're doing. So if you think about what we see in the figure, so basically the R is the way that you just accumulate along the vector function, okay? So basically, when you're doing the Riemann sum, this is actually displacement. So you can think about these, yeah, let me do that, segments. Okay, so if you make a Riemann sum, this is gonna be segments. Or you can think about these as secant line segments along the curve, right? But then if your subdivision is small enough, then you can use these tangent direction tab t multiplying by the arc lengths along each purple segment. Okay? So essentially, you're gonna have displacement starting with the force field, okay? Starting with the force. And you accumulate, that's gonna give you the work done, right? So here, so this is the physical meaning of the line integral along the curve. What is the remark? So here, we have a differentiable cap C, right? But then if you have a curve C that is piecewise smooth, then we just add up the integral along each smooth piece, right? So if it's piecewise smooth, there's a union of smooth curves. C1, C2, all the way up to Cn. Then the line integral on the entire curve C of FDR is exactly the line integral along each piece. So here we can have really piecewise smooth curves. So this could be C1 and then C2, and you travel along C3 and then finally C4. Okay. So C can be it consists of 4 different pieces which are piecewise smooth, right? But then it's the similar logic to the physical sense that you accumulate along every curve. It will be the work accumulated from the initial start point right here to the end point right here. Right? Remark. So now you see that so for a curve, it always has a start point and an end point. Here, we assume that the orientation of a curve C is corresponding to the increment of the parameter. It's basically, so even if you're along the same curve, but if you just start from the opposite direction, from the other endpoint to the target, okay, so that's the opposite direction, okay, that's a different orientation. So let's say we have a curve like this. And we have, so this is a vector function, but on the left hand point, we have the location associated to, let's say, t equals to a, and then on the right hand point is c equals to b. Okay. So basically the parameter goes from a to b. Okay. So the positive orientation is this one that's going from the left to the right along the curve. But if you parameterize it a little bit differently, then essentially you can negate this direction. So basically, so if you have t equals a, it goes from t equal to b, then that's gonna be from r of a. That's the starting point and the ending point is r. Okay, so that's this orientation, that's c. Okay. And if you just negate the direction, this is gonna go from the left to the right. Okay. From the right to the left. Like this. So this is actually the negative direction of c. And you can think about it as a different parameterization, right? Because essentially, okay, so R of A, R of B, so it goes all the way to the right, right? But then if you do it in a different parameterization, you can think about making, let's say, just U equals to A plus B minus T. Okay. So this is the so basically you are using the same vector function, but then you just parameterize it in a different way. So this is A plus B minus, well, so this is we can name this not a function. Let's say T of U. Okay. So here you're just using another parameter U that is so T of U represents the parameter that you have that you plug in into the vector function. Okay. And now U also goes from A to T, A to B. Right. So basically, when U is A, and then this T is going to be A plus B minus U, which is of course B value, which is going to be right here. Okay. So this is where U equals to A. This is where U equals. Right. So now you can see if you parameterize it a little bit differently, then the orientation is definitely different. Okay. So now because the increment of your parameter U, the new parameter will be like from here to here, and then from here to here, and here to here, like these. Okay. So this is the opposite orientation. Right. So here we have. So basically, we can expect that the different orientation, the opposite orientation that you choose, then you will negate the side. Okay. So if you go along negative cap C, so the force field will stay the same, but dr is opposite. Okay. So that's the difference. So this is actually the negation of the integral from the original orientation. For any vector field and the curve caps. So you can see that the key point for Cap C, the parameterization actually relies on how you parameterize your curve and the parameter that you choose, the variable that you choose. Okay. Remark? So now we can see, as long as we define these vector field and the curve C nicely, then we'll be able to calculate the line integral. Okay. So we know one way is we write cap F, the vector field starting with the unit tangent direction along the curve, accumulating with respect to length, right? And then this is equivalent to F starting with dr, right? And we further know the way that we calculate this line integral, which is the definite integral from A to B of F. So basically, we just now utilize parameter T. So this is the evaluation along the vector the curve, okay, starting with prime dt. Okay, so writing down the differential explicitly, but also we realize for the left end, this integral actually equals to. So if we write it in terms of the parameter t again, so basically we know ds is the something that we can translate. Okay, so basically we have f starting with t. This is actually a scalar, right? This is actually a scalar which results from the inner product, dot product. So ds we can rewrite it as the magnitude of r prime times dt. Okay. So now we realize that the line integral defined in this way, these are just scalar functions which are dot products between the vector field and the unit tangent direction along the curve, right? But then if you think about making these scalar functions as just let's say constant one, right? And then you're just integrating along the curve, which is calculating our path, right? So basically, we can say the above line integral is actually a special case of accumulating a scalar function along the curve, accumulating with respect to dot length. Okay? So recall if you accumulate one along the curve, with respect to dot length, this is exactly accumulating one multiplying by the magnitude of the tangent direction integrated with respect to t. Okay, this is exactly the arc length. Of curve. Therefore, so basically that circle part, which is also the constants in red. Okay. So for the red part, we can just replace it by whatever scalar function that we have in the three-dimensional space. Okay. Therefore, the line integral of f starting with the unit direction cap t, accumulated with respect to the length is nothing but a special line integral which we say this accumulating along the curve of f of x, y, z ds, okay, where we just specifying the scalar function little f to be the inner product of the vector field starting with the unit tangent direction along the curve, right? So this way we can just define a line integral exactly using the general linear function definition. So in general, the line integral of little f of x, y, z over a curve FC is basically the integral along the curve C of little f accumulative with respect to the arc length, right? So the way that you compute is that, okay, still we just recall that for cap C we have the parameter t that's the way that you parameterize your curve. Okay, so this is going to be translated to t. So basically x, y, z they will be related to the coordinates of your vector function. Okay, and then so ds is going to be replaced by the magnitude of r prime dt. Okay. And of course, this part, so this is, if you write it in another way, this is just saying, okay, I have the function, originally I have f of x, y, z, right? But basically, x, y, z, they have their different characterization when you're using the variable t. So basically, this is x of t, y of t, z of t. Right? If you really want to specify the coordinates without using the notation of the vector function. Right? So this is the line integral along the curve. If you have a scalar function that you're accumulating. So this is the most general case that we can write for the line. So basically, recall that in the case that the scalar function is 1 everywhere along the curve, then you are just looking at the integrand of 1. Okay? So recall it's really similar situation if you are just having the double integral over a general region D, accumulating the tiny little increment area, right? So that's the area of the entire region D for the double integrals. And then for triple integrals, we have seen that basically if you accumulate over the entire solid the tiny little increment of the volume, that's gonna give you the volume of the solid. Right? But here, similarly, if you now are looking at the line integral along a curve C, and you're incrementing with respect to the arc length, that's gonna be the arc length of the smooth curve. All right, so now we have defined this line integral for a general scalar function along the curve. And let's look at an example of calculation. So now let's say we have a curve and we're integrating along the curve of 2x ds. Okay. So 2x is now the scalar function that we're integrating. right? And then we just need to specify the curve, and then we need to somehow be careful about the way that you accumulate along the arc length. Okay, so basically, of course, we don't really calculate that. We just use that the magnitude of our prime dt, that when we have the parameter t there. And then we just need to specify the smooth curve. Well, it doesn't have to be smooth, it could be a piecewise curve. So the curve is the following. So it's defined by the picture below. So basically, in the xy plane, so the curve C, it starts at the origin, right? And then at the beginning, it will travel along the parabola, which is y equal to x squared, from the origin to the point 1, 1, right? And then after that, it's gonna vertically increase all the way to the point. I think this is 1, 2. Okay, so you can see, okay, this is definitely a continuous curve, but it is not differentiable at the intersection of the two pieces, right? Okay. So here we see that we need to separate the line growth into two pieces. So here we have that according to the figure, cap C consists of two pieces, C1 and C2. So C1 is the parabola part. And C2 is the vertical line part. So for each piece, we need to decide the parameterization, all right, and then we can write down the interval. So for C1, it is the part of parabola y equal to x squared, where we have axis between 0 and 1, right? So we can think about the natural parameterization where you just use t to be x, okay, from 0 to 1, right? Hence, we can define C1 by the following. So we use the vector function. So C1, we call this vector function to be R1 of t. And basically, we just choose t to be x. Okay, so basically x is t, now y is just going to be x squared, which is t squared. And we just write it down. Okay. Here we set t to be x. Right. And we do have a range. So here, since now t is just the original x from the figure, then t is also between 0 and 1. Okay. All right. So that's the parameter part. So that's the parabola part. So it starts from the origin to the point 1, 1. Okay, that's C1. And then C2, so far so good was for the first part of the curve. Okay. So if this is clear, then the second part is this piece, which is the vertical part. Okay, so you can see, okay, now the x coordinate doesn't change, or only the y coordinate changes from 1 to 2, right? So then you can think about, let's say, okay, let's just make the y coordinate to be the parameter, and then it just increases from 1 to 2, and the x coordinate will not change. Okay. So we just put them down. So for C2, it is part of vertical line x equals 1, where y is between 1 and 2. And it can be described so we just name it as the vector function of 2. But then here, so the only thing that's changing is y coordinate, right? So we just that should be t. So the x part is always a 1, so that's just I plus, now this is tj. So t is just is the y value here. Okay, so this is just specifying that x value is always 1 and y is t. Okay. So now since y is from 1 to 2, then t here is also from 1 to 2. T goes from 1 to 2. So okay, now we have the specific vector functions defining each piece C1, C2, and then we can write the line integral specifically, okay, according to the definition here. Okay. Hence, the line integral over the entire curve C of 2x ds. So this from the previous one of the columns, we have the line integral over the entire curve is going to be the sum of the integral on each smooth piece, right? C1 is 2. And then, okay, in terms of the C1, the integral, so we just write in terms of t now. So realize that this is, so basically t goes from 0 to 1. So we do we put the definite integral there. And then now x value at the curve C1 above is right here, right? So x value is 3. Okay. So this is actually 2 times t. That's 2x. Okay. We evaluate along the curve. Right? And then ds. So ds, this is a parameterized curve. So we write R1 taking the tangent direction. Okay, and also take the magnitude, and then dt. Okay, and then we specify this magnitude a bit later. And then now for C2, we also just write down the curve. But now, so C2 is nice. It's easy in the sense that only the y value is changing, and then x value is always a 1. Okay, so we just directly write this is going to be 2 that we accumulate along the C2 subpiece, right? And so here, this integral is not going to be simple because now x value is not changing. You're essentially accumulating a constant, right? If you pull this out, you will have what? You have 2 times plans of C2, right? And C2 is a line segment. So that's actually very straightforward. We don't even need to do the further calculations there. Okay? So let's put the things down. Yeah, we will still want to keep R1 there. So this is equals to from 0 to 1, 2t. And then for the magnitude of R prime, R1 prime, right? So this is going to be the square root of the the derivative of each component squared, right? So the derivative with respect to t for the first component is 1. We square that. And then for t squared, that's the second component, we take the derivative, which is 2t, and we square that too. Okay? So that's the magnitude for R1 prime. And dt there. And like we said for the second part, this is 2 times the line integral along C2 accumulating our plans. Okay? And now each piece we know how to calculate. The first one, although this is radical, but now under the radical we have what? We have 1 plus 4t squared. Right? But on the outside, this is t dt that we can use substitution. Okay? So realize this stepping integral from 0 to 1 of 2t, and under the radical we have 1 plus t 4t squared dt. Okay? So this is definitely something that we can integrate by using u sub. Let's recall that we can set u to be 1 plus 4t squared. So du is going to be at dt. So 2t dt is what? It's actually 1/4 of du, right? So this part you can handle it. Okay. And now for the second integral, this is 2 times. Now the arc length along C2. Okay, but basically we're just moving vertically up. Okay, from the point 1, 1 to 1, 2. So the arc length along that C2 is actually 1. Okay, length of the line segment. That's good. And then we just evaluate. Okay, so make sure to double check. And the final answer for this should be 5 square root of 5 minus 1 over 6. So that's the answer for this first integral, and then for the second one, it's just 2. Sum of these. All right. So so now we have defined the line integral over a curve. And we also involved the vector field, right? For in general, we have, if you are given the vector field, this is vector field dotting with dr. Okay. Or if you're given a scalar function, you're just accumulating the scalar function along with it. Right? But here we're gonna give one more remark regarding the geometry of the line integral of f of xy accumulated along the arc length of the curve. Okay. So we are still able to somehow illustrate it in the three-dimensional space if you only have a bivariate function. Okay. But if you have a three-variable function, then this is something a little bit more complicated. Now let's see. Let's say we have our t in the two-dimensional space. This is just basically a curve in the xy plane, right? And here we have a parameter t. This is a curve in R2. For function f of xy that is non-negative, and the curve of t equals to the vector of x of dy of t in R2. So if you think about it, this is actually accumulating the non-negative function, right? So if you treat f of xy to be z, right, as a surface within the space, then actually you are accumulating this elevation along the curve, right? So we have for line integral of f of xy, yes, this is by definition the definite integral with respect to t of the evaluation along the curve multiplying by, so the way that you accumulate along the curve, right? Length part. So here, basically we are accumulating that elevation, which is f of xy, which is non-negative, right? So that part is essentially a surface. If you want to sketch a figure, so basically we may have a curvy surface on the top. Okay, so this is where we have that f of xy. Okay, so this is the surface on the upper half of the space where f of xy is non-negative. Okay, and then now if you think about that curve C, this curve lies within the xy plane, so it should be a curve somewhere like this. Okay, so within the xy. And depending on the orientation, let's say this is the starting point on the left end, and on the right end you have the ending point on the right. So the orientation is here. Okay. And then basically, now if you think about this part, okay, the evaluation of the function little f along the curve is actually what? It's actually, you can say this is kind of like a curtain. Okay, so going vertically up, that's intersecting a surface. So the evaluation, this is exactly vertically up. So let's say for the left hand point, it could be, the evaluation could be somewhere like right here. Okay. For the one here on the right hand, it could be somewhere like right here. Okay. So basically, this evaluation will form you a space curve in a sense. So basically, this curve C defines you the xy value, right? But then the z value is relying on x and y on the surface on the top. So it could be something like this. So we don't really know what the exact appearance of this curve in red, but when you do the evaluation, it could be like this. And now if you think about the definite integral, okay, so basically in terms of the Riemann sum, you're actually picking sample points along the bottom curve, right? So it will give you vertical evaluations up, and you are accumulating just these dashed lines as heights, right? So basically, you're accumulating all these heights, even ds, which is the length, the arc length along each subpiece. Okay. So now if you think about it, basically the height is actually what? The height is actually the length of this kind of a strip, right? And ds is actually the width. Okay. So essentially, for the line integral, you're actually accumulating the vertical these vertical strips, okay, so which is the area of what we call a curtain that you see right in front of you. So that's the curtain right here. The area of the curtain is the, well, you can say the physical meaning of the line integral. Okay. Which is integrating f of xy along the curve, accumulating f length. Right. And of course, we specified that this bivariate function should be non-negative. So essentially, these lengths of the vertical strips, they are non-negative. Okay, so essentially you can accumulate and it makes sense. Right. Okay, so this pretty much finishes this section on line integrals.